Welcome to week 2 of your organic chemistry lab online. And this week we'll be discussing melting point. And for your textbook and reading material, we want you to cover sections 8.1, which encompasses pages 84 to 89. So this will be a pretty quick overview of melting point, what it means, some unique properties of it, and then we'll discuss the quick experiment we would have covered in lab, how to use the DigiMelt melting point apparatus, and that'll be about it. Okay, we're going to begin with a quick overview of what melting points of a solid are, and just a little bit of talk about the intermolecular forces and what determines vapor pressure. So for melting point, we're generally only concerned about a solid, and melting point is the temperature at which the solid and the liquid phase of whatever your substance is will exist at equilibrium. In other words, the melting point is the temperature at which the solid and liquid have the same vapor pressure. So they're at equilibrium, they're fighting each other to be solid liquid, but everything's happy, same temperature, same pressure, everything's good. And that's considered the melting point. So vapor pressure, if you've forgotten, is the pressure exerted by any substance against air. So both liquid and solids have vapor pressure. Technically gases do too, but we're not dealing with gases, they're already in the vapor phase, so we're only really worried about solid and liquid because it's the gas already, it's already melted, so we can't quite determine the melting point just from a gas. So generally when you put temperature or heat into a system, the intermolecular forces that bind the matrix of the atoms start to cause those atoms to vibrate. And the more kinetic energy you input, the more they vibrate until finally those attractive forces can be overcome and it breaks apart and it leads to disordering of the solid. And that's basically what melting is, a disordering of the solid caused by a temperature increase versus the current pressure of air. Now, when we're talking about melting point ranges, that's generally of a pure solid. What we're going to be discussing in this lab is the melting point of a system where you have multiple solids or impurities in a solid. So when you do a melting point for a pure substance, it's generally you express as the lowest temperature range when the solid starts to melt. It's not an exact point, it's a range. So basically when you're taking a measurement, you see when their first little bit of liquid starts to form and that you have the start time there, and then when the whole thing turns to liquid, that's when you end your timer. And that range is your melting point range. So when you're dealing with a pure compound, it's got a very sharp melting point. Usually within 1 degree Celsius is the time it takes for the beginning of the melt to all of the melt, just 1 degree. But if you have a contamination or a mixture of different substances, you get a couple things that might happen. So the melting range definitely becomes more broad. You get any 2 to 3 degrees centigrade is how long it takes to fully melt. It can even take longer depending on how many impurities or differences in the type of compounds you have together. The other thing is, and this is always the case, when you have a mixture or impure compounds, the melting point will always be lower than what it should be for the pure compound. And this is called the melting point depression. And we'll be talking about that in the next couple of slides. Okay, so for a mixture of different substances, we can say we'll have a solid A and a solid B in our example here that we've got on our screen. So solid A is going to be contaminated with solid B, but depending on the percent contamination of solid B and A, the melting point is going to change. Now we can graph all this. You would take a bunch of measurements using known quantities of these substances, and you would make a graph of the melting point versus the percent compositions of each of your two compounds, A and B. So what we're going to look at is on A, if we have pure A and pure B is non-existent in this case, and the letter A, you notice that it has a specific melting point, and as you start increasing the percentage of B in A, it starts to dip down. It dips all the way down to point E. And then as it goes to the right further on the graph, you start getting more and more concentration of B until finally at the very end you have pure B. So on the far left you have pure A, on the far right you have pure B, and that dip point that's labeled E, that's where you have the lowest temperature, and that's very, very important. So the thing to note as the lowest melting point temperature of a mixture of different of different components like we have in this case. That's called the eutectic point. Eutectic, E-U-T-E-C-T-I-C. And also this is called the eutectic mixture. The mixture in this case, if you look at the graphs, is 60% A, 40% B. So that is basically anytime you have two different contaminants together, two different substances, the melting point, like we said earlier, is always going to be depressed, and the lowest temperature that you can get out of it is called the eutectic point. And you can figure that out by doing a bunch of different experiments, varying your percentages, and graphing them, then finding where that lowest point is, which in this case is 60% A, 40% B. All right, so for the lab we would be doing this week inside the actual labs, if we had them, we're going to be determining different melting point determinations of combinations or pure versions of two different solids. The two we're going to be using, the substances are going to be benzoic acid or 2-naphthol. On the top right of the screen, you can see the benzoic acid. It's a kind of a flaky white powder, which is what most of your organic compounds are going to look like. And it melts anywhere from 121 to 123 degrees Celsius. And to the right of that, you see 2-naphthol, and that's kind of a brownish dirt. The flakes are kind of flat. That also melts at 121 to 123. That's why these two are chosen. For this lab, they're chosen this way, and then you can also see, because one's white, one's brown, you can see you have a contaminant, and you can basically eyeball the percentage of how much you have in there versus, pure substances. So what you would normally do is you're going to make a set of 5 different capillary tubes filled with specific varying amounts of these two substances. So for your first capillary tube, you would be using just pure benzoic acid. Then you would go 10% 2-naphthol, 90% benzoic for your second. Your third capillary tube will consist of 50% of each. Your fourth will then switch to 90% 2-naphthol and 10% benzoic. And then your final capillary tube will have 100% 2-naphthol. So once you have all of these done, then you're going to start using your what's called the Digimelt melting point determination apparatus. It's a little black box with basically a tiny magnifying glass in it, where you can actually look directly into the bottom of these capillary tubes and see when things are melting. So what you're going to do for this specific reaction, not reaction, it's an experiment, you're going to take these capillary tubes and you're going to have 2 different dishes, one with your benzoic acid and one with your naphthol. So you scrape the opening of the capillary tube into your substance and you get a little bit in there. And once you have that in there, you're going to tap it very lightly on the desk or the counter to compact all of that powder on the bottom. So the best thing to do for this particular reaction is to mix these up beforehand and make sure they're all mixed up nice and well, because we don't want areas of one versus the other. We want a nice mixture. And then make each of your individual capillary tubes by scraping them through the solid and then slowly tapping it. You want about a centimeter worth of packing height of your chemical at the very bottom of the capillary tube, because that's about all that gets seen in your melting point apparatus. So you make sure it's compacted and down there, and you don't make sure you don't have a lot of air pockets in between. So you're going to do that for each of your 5 capillary tubes using the percentages we've noted on this slide. And then now we'll move to the next slide and we'll show you how to use the actual melting point machine. All right, once you have your 5 specific capillary tubes all hooked up and ready to go with your substances inside of them, you're going to turn on the Digimelt apparatus, which we show here on the upper left. That's what it looks like. At the very top of it, top left, you notice the little eyepiece. That's where you look to see the things melting, and you can see there's 3 capillary tubes in it. That very top metal part there under the grate, where that yellow arrow is pointing down, it has 3 holes where you can put capillary tubes down in there. And you got to slide those all the way down, and when you look through the glass, there's a little light that shines to the back so you can actually see it. And what you're going to do is you're going to set a climb rate for the temperature, and then you're going to set it's called a ramp rate, and then you're going to set a hold or temperature, something around 80 degrees Celsius is what we're looking for. So the best thing to do for this specific reaction is to just do a 5 degrees Celsius per minute rate up to around 80. And then at 80, because you're getting close to the known melting point of these compounds, you're going to ramp it up a lot slower, 1 degree Celsius per minute. So that'll make you, when you're looking at this, you can actually get a good time other than it going too quick and just quickly melting and you not being able to see. So once you have that all set up, you would hit start. It's the green and red button there, and it would start climbing. And basically, once it gets to around 80, you need to constantly be looking in that little eyeglass to see when things start melting. So on the bottom of this slide, you can see what these things actually look like. So on the far left bottom, this is called the onset of melting. This is when you would take your first temperature measurement, because you can see the crystals, especially on the top and then some on the bottom. They're not as bright or reflective. They're more opaque. So that tells you right there that they're starting to melt a little bit. And sometimes on the bottom you can see a little pool of liquid form, but that's when you start recording the starting temperature. And you just keep watching it. As the middle, it progresses a little bit. It's definitely melting, but there's still some solid in it. And then finally at the right, everything's melted, and that would be your end recording temperature. So your temperature range would be when you first started seeing the melt, which would look like the bottom left, to the final melt when everything is melted on the bottom right. For this, because we're using, unless it's one of the 100% benzoic or 100% naphthol, we already know it's a mixture. So they're going to have a longer range. It could take 2, 3, maybe even 5 degrees centigrade. So you might need to be watching it for a while, but you would always just watch it, record the initial part, record the final part. Okay, now we have all of our data. You've looked at all 5 of your capillary tubes of your known compounds. You've recorded when the melting begins and when the melting ends. And we would need to take this data and plug it into some type of spreadsheet. Excel is the quickest and easiest to use. Most people have access to that. And then you're going to plot it. So for this specific thing, what we're going to look at is the table up top. This table is what you're going to have all your data in. You're going to be recording the beginning point of your melting and the ending point of your melting. So when you graph this, you're going to have 2 different lines to graph. You're going to graph the beginning melting portion, and then you're going to have a separate line that's going to graph the ending point. Now, if you look at the little chart we have below with some just random data that we put in there just to show you how this works, the blue line is where your melting begins. So that's the first reading from all 5 of your capillary tubes. And you can see it goes down to a central point and then kicks back up. That's what we expect, because the third set is when it's a 50% mixture. So we can tell that, as you get more and more contaminated, the melting point decreases, which is what we expect, and luckily our data fits that. The second line, the red one, is when the melting ends, and it also goes down, but you can see it goes down at a much steeper rate than the blue line. So that also shows that the broadest melting point range is what we're looking for. That's that eutectic point, that is because it's the lowest point of temperature. So what you would do is you just match the 2 points that are the lowest, draw a line between them, and then trace across to figure out that temperature. So for our specific data here, we show that about 90 degrees Celsius would be our eutectic point. And because that matches with the third data points of both the blue and the red line, we can say that our eutectic mixture is, for our data at least, is a 50% 2-naphthol, 50% benzoic acid mixture, and its eutectic melting point is around 90 degrees Celsius. Now this is about right. You would just kind of thinking this, looking back at it with common sense, because both of these molecules melt at from 121 to 123. So they have a very, very similar melting point. So if you have a mixture of 2 similar things, the 50-50 ratio should have basically the lowest melting point. It's just a common sense thing, and it matches with our data what we have here. So this is what you would do. You would take your 5 readings, so melting beginning, melting ending. You would plot 2 different lines, one from the beginning melt, one from the end melt, and then you would just eyeball it, find where the lowest points were, trace across, and determine the eutectic mixture and the eutectic point. Now, were you in an actual lab, you would have cleanup and waste disposal to think about. So you might be asked about this on the quizzes at the end, so we'll cover this real quick for you. You're going to have leftover benzoic acid, 2-naphthol. You might have a couple mixtures of it here and there. You're going to have either watch glasses or weighing papers that has the dust or any type of contaminants on it. And you're going to have those little capillary tubes that have your 5 different mixtures in them. So any of the solid waste that's left over, even though it might seem wasteful, you throw it away. And it gets thrown away in the solid waste container, which is one of the big black bins that's labeled solid waste. and it's generally in the waste fume hood in the back of the lab. Also, that stuff that goes in the solid waste container is any weighing papers or things you use like that that have a lot of contamination on them. If it's just a little dusting and all, you can just tap it out and throw it away normally. But generally, if it's had a chemical on it, the best thing to do is just put it in solid waste, not worry about any weird issues that might arise. So for those 5 capillary tubes, we don't reuse those. They're just kind of like pipettes in terms of that. They're too easy to break, too hard to clean. So all of those, you invert them and tap them again, try to get everything out of it that you can, but most likely you won't be able to get very much out. But those go in the broken glass container, glass waste container. It's the brown box is labeled with broken glass, and make sure, like we said in our safety video, those don't go in solid waste. Those don't go in a normal trash can. They just go in the very specific glass container, broken glass container. For the Digimelt, when you're done with it, of course, turn it off. Make sure it's cooled down. It doesn't get too hot to the touch on the outside, but the inner heating elements could be 100, 200 degrees Celsius. That's pretty hot. So you make sure it's cooled down to room temperature. Then you're able to put it back in the back of the fume hoods and wrap the cord around it so it's not just cord free and dangerous as that would go. And then just make sure any spills or anything you have might be cleaned up, and just a quick wipe down of your laboratory fume hood area, and that would be it. So just a quick overview again. For this specific lab, we talked about melting point, which is just the temperature at which your vapor and your solid and your liquid have equilibrium, and that temperature is based on the vapor pressure of the air in comparison to the vapor pressure of your solid or your liquid, where they're all happy and equal. And for this specific experiment, since we're using a mixture of 2 different substances, we also have to take a look at the eutectic mixture and the eutectic point. Eutectic point, of course, is the lowest temperature at which your combination of substances or your mixture of substances melts. And the eutectic mixture is the ratio of those 2 or more substances you have at the eutectic point. So that's pretty much going to be it for this lab. Nice, quick, and simple. Be sure you read up in our textbook on stuff covered, because that might be included in the quiz. Take a look over this again, and I wish you the best with the quiz, and have a good week.